The simple example I gave earlier, study hours versus exam score, was mainly used to illustrate a linear relationship. Now I will go step by step to show how the data eventually form a regression line. In this example, we assume X represents study hours and Y represents exam scores. The first step is to calculate the mean values of X and Y. The mean of X is 3, and the mean of Y is 64. Next, we calculate how far each data point is from the mean. We square these deviations and sum them to get the total squared deviations. At the same time, we multiply the deviations of X and Y from their means and sum them to obtain the sum of cross products. The slope is calculated by dividing the sum of the cross products of the deviations of X and Y by the total squared deviation of X. In this example, we divide 75 by 10, which gives a slope m equals 7.5. This means that each additional hour of study increases the predicted exam score by about 7.5 points. Next, we calculate the intercept using the slope 7.5 and the mean values of X and Y. This gives us an intercept of 41.5. Therefore, the regression equation becomes y hat equal 41.5 plus 7.5 times X. We can use the regression equation to predict Y for a specific value of X. For example, when a student studies 1 hour, the actual exam score is 50. Using the regression equation, we can also calculate the predicted exam score, which is 49, and we can do the same for other study hours. A t-test is used to determine whether the slope is statistically significant. First, we calculate the residual sum of squares, SSE, to estimate the variance of the errors. Then we compute the t-statistic, which equals 15 in this example. This value is much larger than the critical t-value of 3.182 at equals 0.05. Therefore, the slope is highly significant, indicating a very strong linear relationship between study hours and exam scores. Study hours can strongly predict exam scores. Coefficient of determination represents the proportion of the variance in the dependent variable exam score that can be explained by the independent variable study hour. The coefficient of determination can also be calculated using the sums of squares. We square the cross product underscore, which measures how X and Y vary together, and divide it by the product of the total variation in X and Y underscore underscore. This gives the proportion of the variation in Y that can be explained by X. In our example, our square equals 0.987, which means 98.7% of the variation in exam scores can be explained by study hours. The F-test evaluates whether the regression model explains a significant portion of the variation in Y. In this example, the calculated F statistic is about 228, which is much larger than the critical F value of 10.1 at p equals 0.05. This means the regression model is statistically significant, suggesting that study hours significantly explain the variation in exam scores. Our regression model is exam score equals 41.5 plus 7.5 times study hours. In other words, every additional hour of studying increases the predicted exam score by about 7.5 points. The R-square value is 0.987, meaning study hours explain nearly all the variation in exam scores. Both the t-test and f-test confirm that this relationship is statistically significant, showing a very strong linear relationship between study time and exam performance.